Welcome to this class on how to model the mechanical behavior of materials. We will primarily be talking about mechanical behavior, but we'll also look at other things. So this is a class on how to take a material and figure out what would be a reasonable model for it. So let's start this thing. So what is this course about? Talk about what are the elements of modeling, what do we mean by modeling, and so on. And we will talk about what are called universal constraints, things that all materials have to meet. Then things that some materials have to meet, and how do we decide how to represent different kinds of materials. And then modeling of different classes of correlations. So this is connected with different types of materials. And this correlation between states is also called constitutive relation or response relation. So the idea is to say that there's some cause and effect. See, that's the basic fundamental, I would say, paradigm of almost all models, which is all mechanical models at least, which is that there's something which causes and then there's something which is the effect, so which is the response. So there's a stimulus and there's a response. So we will have to figure out what would be considered as stimulus and what would be considered as response and how to do it. And then comes the question about how do we run experiments, how do we gather the data, how do we do inference, and all of this stuff, which is elements of this. So we will actually be heavily concentrating on these items and a little bit on the last one. So the idea is you have to figure out what is stimulus and what is response. So that's a big issue there. And the question is, why do we do models? The reason is that we want to gain insight, try out different scenarios, make predictions, and eventually make decisions. So models are meant to be decision-making tools. For an engineer, it's quite a different thing for looking at models for a scientist. The scientist's purpose for a model is for the description of nature. So they will try and create models that are ever closer to nature. Our aim is not necessarily to describe nature, but to make enough model that we are able to make some decision. So we don't try to do very close approximation to nature unless it is necessary for us to do that to make a decision. So that's one thing. They are not meant to be exact descriptions of reality for our models. And one of the most interesting statements by a statistician based on for statistics models is a very good one, which says all models are wrong but some are useful. So the thing is, you cannot say, hey, this model is right. The question is it internally consistent? So what we look for models is consistency and use, whether it serves the purpose that I've intended it for. So please remember that without an underlying purpose, there is no meaning for an engineering model. So you have to know what is the purpose, and then you can do some model. So every model that we do will be start out with some kind of purpose. What are we trying to do? What is the object that we are trying to model and why? After that, we will figure out what to do. Okay, so this is a very important thing. So and by the way, there is not a single model for a given object. So different models for the same. So please remember, different models serve different purposes. There is no single universal model, that kind of thing. We will look at different models and we look at different purposes. So for example, for an airplane, for an air traffic controller, an airplane is a dot in the sky. It's just a particle. When you are close to landing, then the airplane is treated as a rigid body. That is, it has not only position but also orientation. because you want to make sure that it's oriented right for landing on the runway, right? So there's an orientation issue. Once you're landed, and to the mechanic, it's actually not a rigid body. In many cases, it's a flexible, large object, right? So each time, if you look at it, a model for a plane is different. So to the person who is designing the cabin, an airplane is a tube. You're with me? So you have to remember that there is not a single model for the given airplane. So don't say what's the airplane model. That means nothing. Depends on for whom and why. Okay, so that's a very important point. So one of the things about models is the following. We need to choose, the basic idea is that we choose simple models where possible. So you can see that there's in this particular thing, there are a whole bunch of boxes in the background, and there's a tree. The question is, how many boxes are there behind the tree? Right? So that's the basic idea. How many boxes are there behind the tree? So you might have thought, okay, most likely one box. Well, it's possible that there are two boxes. You know what I mean? So the question is, how do you know whether it's one box or two boxes? And what's the choice for choosing? So in figure 1, for example, one box theory does not assume any complicating factors. For example, it does not assume that there could be two boxes, but they just happen to be of the same height. It's much simpler to assume that there's just one box. Okay, and the simpler model, the one box theory, will explain the data. So does the two box theory. But the two box theory requires a coincidence that two of the parameters, in this case the height of the box, have to be the same in order for this particular data to be explained. Those kinds of things are problematic. So the more parameters you have to explain something, the more coincidences you should have in order to explain the limited amount of data. And those kinds of things are dangerous unless you have some other compelling reason to believe it. But generally speaking, they are dangerous. So keep your model simple. Okay, so this is actually a very fundamental thing called Occam's razor, and you should go and read. That's actually one of your assignments. Go and read about Occam's razor. Okay, so in order to make decisions, we always have to make a whole bunch of assumptions. So there is no inference without assumptions. So there is no such thing as a non-parametric model. Even though you will see that the literature is filled with ideas which are called non-parametric, actually what it is that there is some other parameter somewhere else. There has to be some adjustable constants. Otherwise, you cannot get anything. Okay, so there's always some assumption underlying any model. So the question is, you have to make a few robust assumptions rather than a large number of unverifiable or unlikely coincidental assumptions and conspiracy theories. So robust assumptions means it's reasonably tolerant to making different kinds of assumptions and so on, so that it has to be reasonably tolerant and still give you same results. Okay, and on a this kind of idea is there for any time you have a model for anything. So you listen to conspiracy theories where this person did that and all of that, you will see that conspiracy theories are unlikely events because they make a large number of assumptions about coincidental events. So there's a very nice statement about this: do not attribute to deviousness what can be fully explained by stupidity. Okay, so the idea is, if a simple explanation will do, don't try a complicated explanation. So the question is, what do we mean by simple and what do we mean by explanation, things like that. We will see what happens. So models are, in our models are quantifiable representations of reality. So on one side you have reality, on the other side you have cartoon, which is, you can see that I have converted that smiling face into just eyes and mouth and ignored all the other features. So cartoons always exaggerate a couple of features and ignore everything, right? Same way for the other one, you can see I have ignored all the features. and then you convert the remaining features, you try to mathematize or quantify it by looking at eye shape, mouth shape, curvature, that kind of thing. Notice that mouth shape is important because I showed you, an example without the mouth shape. So why can't we just do it with eyes? In this particular case, in this extremely simple model, if you just look at the eyes, you can see that on that side, it's not evident whether which one is laughing, which one is crying. For all you know, the first one does not represent laughing. For all you know, it may represent fright, because eyes are wide and open, like laughing, but also like fright. If you include eyelids and other things, which is a different kind of model, you may be able to explain. But my point to you is, you have to say that I need a minimum number of features in order to explain the events, but I don't need too many features. That's the idea behind modeling.